MVC, it's Ms. Deer. I just wanted to keep going where we ended off in chapter 15, section 1. We were talking about vector fields. And remember that a vector field assigns a vector to every point. And we looked at if we have a vector field in terms of x, y is mi hat plus nj hat. It's conservative if and only if this vector field is the gradient of some function f. If it is the gradient of some function f, we call f the potential function. And before we find that potential function, one way that we can check to see if it's conservative is if this is the gradient, then this is the partial derivative with respect to x and is the partial derivative with respect to y. So if we take the derivatives again, the mixed partials would be equal. So a vector field is conservative if and only if the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. So before we can come up with a plan for deciding if a vector field is conservative in 3-space, we need to define a new function. And we're going to call that function curl f. So curl f is defined to be del cross f. We read this del cross f. And obviously if I have a cross product, we're working in space, so this is going to be for 3-dimensional functions, and we need to come up with what is del. So del is a vector, but it's actually not a vector in itself. Vector is called the del operator. And the way a del operator works is that it's a vector, but it's only defined in as far as it operates on another vector. In this case, it's going to operate on f. So in order to come up with del, thank you, can we not yell please? So if we're going to come up with del, this is my 3rd try on this video, so you're just going to have to listen to me yell at my kids now. Del cross f. We're going to throw this in a matrix. So we have I hat, j hat, k hat. This will give us a vector when we're done. Next, we're going to put the del operator. The del operator is defined to be the partial derivative with respect to x, the partial derivative with respect to y, and the partial derivative with respect to z. And then we have the components of our vector field mn. And in this case, we'll do p. Because we're going to need a 3-dimensional function, f is going to be mi hat plus nj hat plus p k hat. So now, when I look at this vector that's going to result as this, I'm going to get curl f, which is del cross f, which is going to be, well, in the I hat, I'm going to have the derivative of p with respect to y. So I'm going to have dp dy minus dn dz I hat minus dp dx minus dm dz j hat plus my k hat is going to be the partial of n with respect to x minus the partial of m with respect to y k hat. So curl f is itself a function. It's the result of crossing what we're going to now call the del operator with the vector field. And again, curl f is itself a vector, so it's obviously going to wear a hat. So when we talk about a field, we're going to say that our field f is conservative if and only if each of these components are 0. Well, if curl f is the 0 vector, that means that each one of these components is 0, so these must be equal. So the partial with respect to y is equal to the partial with respect to z, the partial with respect to x is equal to the partial with respect to z, and the partial with respect to x is the partial with respect to y. So if and only if all of these are true, then we have a conservative function in space. So let's take a look at what that might look like. So let's give us an example of a vector field. Let's say that f of x, y, z is x squared. Let's do y squared z cubed I hat plus 2xyz cubed j hat plus 3x y squared z squared k hat. So the first thing we need to find is curl f equal to 0. Well, to look at that, we'll go ahead and throw it into our matrix. So I'll have I hat, j hat, k hat, the partial with respect to x, the partial with respect to y, the partial with respect to z, y squared z cubed, 2x y z cubed, and 3x y squared z squared. So now, when I take my derivatives, so in the I hat direction, I'm going to have 6xyz squared, z squared, minus 6xyz squared. So this is 0, so this works. In the terms of j hat, I'm going to take the derivative with respect to x. So this is going to be 3y squared z squared minus my derivative with respect to z, 3y squared z cubed, so this is 0, still looking good. And in k hat, I'm going to do my derivative with respect to x. So 2yz cubed minus my derivative with respect to y, 2yz cubed, which is 0. So because all of the components are curl are 0, my field is conservative, so I can find a potential function f. Now, if I'm going to find a potential function f, that means that this is my derivative with respect to x, is y squared z cubed. So I can integrate with respect to x, and f of x, y, z is x, y squared z cubed plus whatever's on the end. I know that this is my partial derivative with respect to y, so if fy is 2xyz cubed, then f of x, y, z is 2x, y squared, z cubed all over 2. And this must be my derivative, my partial derivative with respect to z. So if my partial with respect to z is 3x, y squared, z squared, my function is 3x, y squared, z cubed over 3 plus whatever. These are all the same, so this tells me that my potential function f of x, y, z is x, y squared, z cubed, plus whatever constants might be on the end. So I'm going to stop here and before I go into another example.